then afterwards, like once we stop streaming, like I think it's going to optimize the quality.
Okay.
Oh,
Yeah, it looks a bit frozen on my side, actually. Do you still see me?
Yeah, I can see you.
Okay, looks better now. Yeah, fine.
People can let us know. But anyway, ladies and gentlemen,
okay,
another
cool.
deep dive session. I have the honor to be with Antonio Di Caterina today from Tofy X, and we'll talk about the future of engineering design with Tofy X. So without promising too much, I think the stage is yours, Antonio, so let's delve into it.
Hi, Jousef. The pleasure is mine, and actually, thank you a lot for inviting me. It's really a pleasure being here today. I probably think you get this a lot, but I must confess I've been following you for a long time. I probably was still a student at university when I came across your profile, and you always share great content, both super interesting and visually really great. So yeah, for today's deep dive session, I'd like to talk with you and also with the audience about how ToffeeX is transforming the future of engineering design. So what we're doing, how we're doing, and how we envision also the evolution of engineering moving forward. Before we get into it, a few words about me. So hi everyone, my name is Antonio. I have a background in aerospace engineering. I completed my studies in Italy, then I moved to London when I joined ToffeeX. Actually, it's been already almost 4 years that I've been working with this company. And when I joined, the team was very small, just 5 people. Now we're roughly 30 people. And the name was Tofy AM. Slightly different. I can touch on that a bit later if you want. The idea of today is just about, as I was mentioning before, talking about how the future of engineering design is evolving. And I believe that today engineering landscape, companies are increasingly embracing what is called as computational design. So it's probably the right time also to start thinking about the role the engineers will likely have in the future. So moving forward in this new landscape. At ToffeeX, coming back to me, I'm responsible for customer success. But as you know, in the startup, what they say about them is that you wear many hats, and it's really true. So one day I'm supporting customers on developing a super cool, super efficient heat exchanger design. And the day after, I'm sketching the design of the booth for the next event. But it's all fun in the end, so that's part of the game. That's about me, but what about ToffeeX? So what we do at this company. I often like to start by addressing the elephant in the room and say, so why Toffee? Why naming a high-tech company after a candy? The fun fact, or maybe the sweet fact about the name is that it's actually an acronym, and it stands for Topology Optimization for Fluids Engineering, which also tells a lot about what we do. So we are empowering engineers and designers to create innovative and more efficient design for complex thermal and fluid management applications. So this is what we do. We optimize, we help companies optimizing components, devices, systems to improve the efficiency of their thermal and fluid management systems. I don't know if you have any questions before we move forward.
No, not so far, Antonio. I think that was a very good
introduction. That's fine.
Let's just delve into the tool.
Okay, that's great. So why did we start in the first place with this company? So the idea is that we are trying to target what we believe is one of the main issues of the engineering design workflow. The traditional design process goes through a lot of steps, which takes a lot of time. So typically, design process in an engineering company can span across several months or even years, because you have to start by gathering requirements. This might be requirements from either external customers or internal customers. Then you have to start sketching an outline, so come up with a conceptual design. Then you get to a design phase, an actual design phase. Then you have to do testing, simulation, and so forth. Typically, there's a kind of a bottleneck between the design and the simulation. So before you actually get a product to the market, it takes a lot of time. So what you do is to design a component, then the designer will pass this device to the analyst, and they will give you a result. So is this part behaving well? Is performing fine? So are we reaching already the optimal? Are we satisfying all the requirements? Typically, it's never like that the first time. And that's because what engineers do is to take a design and trying to improve it marginally. So, of course, we built a lot over the past years. I mean, engineering is based on the idea of not reinventing the wheel. So if something is working, let's try to make it slightly better or just improve it. But this iteration typically takes a lot of time. And the issue here is that this might also limit the exploration that engineers can tap into. So if you have every time design a component, then go to the analyst, see what is working, what is not, redesign it again, repeat this cycle, and at this point you will, let's say, exhaust your time resources and also your monetary resources. So you have to go to the market, even if that your design is not the optimal solution. Jousef, I can't see you anymore. Probably you can still hear me, but maybe it's just a connection issue on my side. I hope so. Let me check my connection. I think I lost you. I don't have any way to confirm if you're still listening or not. Okay. I think I must still be connected, but I can't see anymore. That's fine. So as I was saying,
I'm back. Can you see me again, Antonio?
Okay. Okay. Yeah. Now I can see you.
I think
that's fine.
Okay. Perfect.
I lost you for a while. I wasn't sure. Okay. No worries. Okay. That was not me. Great. Okay. Cool. So as I was saying before, the traditional design process limits the possibility that engineers can create new and more efficient designs. So they are often the traditional methods are constrained also by legacy tools and processes that limit the possibility to explore new design spaces or to innovate beyond the established norms. This doesn't necessarily mean that the product that comes to life in the end is bad. So in the end, the product at the end of the design cycle will also meet the requirements, but maybe it's not the optimal solution. It's not also the most sustainable solution in a sense. So this iterative process is what we are trying to address and to solve with ToffeeX. So that's why we are trying to propose a new way of designing, which is transforming the approach engineers will take moving forward. So we don't want people to spend time doing countless iterations before they get to a design which is performing as expected. So we want them to be empowered to just make high-level decisions. So they should be thinking about, I need a component that is performing this and that. So I'd like to dissipate that much of electric power, for example. I'd like the pumping powers to be this low. And then it's up to the software to come up with the right solution. So if we have to find a spot where I should place ToffeeX, it would be exactly in between a CAD and an analyst team inside the company. So we are exactly in between these two teams. We are not replacing either of them, but more tools and more possibilities to come up with more innovative and efficient solutions. I probably said just a lot of words, but maybe showing that in a live demo is more efficient. So I will share the screen so I can show you a live demo of the software and guide you through a setup process. So how you would design a component using the software instead. So let me share the screen. Let me know when you can see. I think it's already live.
Yeah, I can see it.
Okay, so this is our web interface. So ToffeeX is a cloud-based platform. We do what it's called today. The way we define what we do at ToffeeX is physics-driven generative design. This means that we are using physics simulation combined with topology optimization to create optimized components. We do all this in a cloud-based platform, and that's because we believe that the cloud is probably the future moving forward in engineering. So it's a good way, let's say, to hand over the resources, the computational resources, not to an HPC local cluster, but to something in cloud. So more companies can adopt these tools and then can join the new trend with the engineering design optimization. So after logging into the platform, this is what you will find. So these are our home page, which is also what we call the project page. As you can see here, we have a list of different projects. They can be thought as folders. Fundamentally, inside each of these folders, you will find all the tools that you need to carry out a design optimization. As you can see, I already have created a new project for this deep dive session, and I'd like to show you how to set up the optimization for a liquid cooled heatsink, which is a classic application, and it also shares a lot of commonalities with other thermal and fluid management devices. In general, when you want to start new, you will simply need to click on here, create a new project, give it a name, and you're good to go. In this case, just to save some time, I made the folder before. You will see here some of the designs that we have been working on so far. Sorry, my connection not the best. Let me reload the page. So here is, okay, I was in, then out again. So here is what the page inside the project looks like. So as you can see, we have a split between an upper section, which includes domains, and a lower section, which includes the toolboxes. If I had to explain what a domain is what we call the computational domain. So the computational domain is effectively the space the designer or the engineer is providing into the software to create the virtual environment inside which the software can operate, Tofy can operate. In fact, the computational space is describing both the physical space inside which the physics of the problem can be solved, but it's also a set, let's say, the space inside which the software can build a design. As you can see here, I have two different domains and I have two different toolboxes. If I click on the domain, you will see that fundamentally what you need to provide as an input is a very simple shape. In this case, we are providing the outline of a liquid cooled heatsink, so how it would look like. So what we have here is very simple shape. So the domain that we have uploaded is fundamentally a triangulated file of mesh. So the input that typically needs to be provided into the software is an STL file, which can be exported out of any CAD systems nowadays. Here you can see it's a very small geometry. So we're talking about smaller than 5 centimeters per side. So it's a very small liquid cooled heatsink to cool down a CPU. What we identified here are a few basic regions or a few basic surfaces that will be used to set up the physics simulation problem. As I was mentioning before, the software is physics driven, so we need to describe the physics to tell the software how the part is behaving, how it's performing, and to inform the optimization process to go in the right direction. In this case, what we had to do was to define an inlet region that you can see here. Over in, you can see the surface being highlighted, an outlet region on the other side, and then fundamentally we also specified the region from which the heat is applied. In this case, the power coming from a CPU. Once we have defined our domain, we go back to our project page, and what we have to do is to build a toolbox. So a toolbox is what I will define as the main operational environment within the platform. It's containing all the tools that you need to perform either simulations or design optimization. To start, it's very simple. You click on create a new toolbox. You can give it a name. So let's give it deep dive toolbox, for example. And you select the domain that you want to use to run this design optimization. Here you have some physics model that you can select. So for example, in this case, we will be solving both a thermal and a fluid problem. So you can select exactly thermal fluid and click on create. I don't want to take too long to show how the creation of the toolbox and of the optimization works, but fundamentally what you have to do is to create one run, which is a design run in our case, because we are expecting the software to output a design at the end of this process. Classic things, we can give it a name, we can set up settings for both design, simulation, and mesh. Because again, I'll say it again, the software is simulation driven, so we need an underlying physics simulation to inform our optimization process. Once you click on create, you will see that here on the sidebar, you have the option to fill in the run details. So all the parameters that you need to input to start the optimization process. And this will, at the end, once everything is set up, you will be able to perform an optimization. So just very quickly, I would like to show you how this works. So first of all, let's start with the mesh settings. It's the easiest one. Here we have to discretize our domain. So give it either a number of cells or specify a maximum cell size. In this case, let's keep it to default. So just to keep it with the basic settings. Under simulations is where we define our CFD problem. So here is where we are specifying all the conditions that describe the physics we are trying to solve. So first of all, for example, we want to tell the software what is the fluid being used in this case. So what is the coolant that we're using. As you can see, we have a list of predefined materials or predefined fluids as well. In this case, just to again speed up this setup, we will select water. as a process, and click on update. For the boundary conditions, what we have to do is to define the boundaries for the problem. So, of course, we want to start by defining an inlet. Here it's very simple. So we can go define the boundary, specify what is the velocity of the fluid going inside our domain, what is the temperature of the fluid going inside the domain. And then once we have identified the patch, we can click on create. This policy was what we follow also for the other boundaries. So in this case, we will define a pressure outlet. So simply identify the boundary. Then we said that we are providing some heat, so we want to cool down this geometry. So what is the power we want to input? In this case, actually, I'm going to do something slightly different. So instead of providing a heat flux, as you can see here, you have the option to apply a heat flux. I will fix the value of the bottom surface that I identified before as heat, that you can see here, at a quite high value. So the reason is that this could be, for example, let's say 340 Kelvin to symbolize, for example, the maximum temperature that the CPU can withstand. So I might be optimizing in the worst condition possible, and then I can run the validations to see also how this is behaving also for different working conditions. So this is one approach that you can follow. The software is giving me this icon, so it's telling me that I still need to input a few more constraints, a few more boundaries. In this case, what it's asking me is to define the boundaries for the remaining surfaces of my domain. In this case, I will just use an adiabatic condition. So I'm making sure that the only heat transfer is happening between the system, the heat provided into the system, and the coolant that I've defined using the inlet here as a boundary. Then we come to probably the most interesting part of the optimization. So here is where we define the settings for our design. As you can see, we have, again, a few parameters we have to always input for the software to successfully run a design. The first one is the material. In this case, we will be selecting a default aluminum and click on update. And then on the objective is where we define how the optimization should be carried out. In this case, as we were mentioning, Tofy is a software to maximize the fluid and thermal efficiency of a device. So what we want to combine is something which is minimizing the pressure drops. So we want to minimize how much energy we need to pump the fluid through the system, but also at the same time to maximize the transfer. These two objectives are in contrast. So if you minimize pressure drops, you also the more you minimize pressure losses, the lower you can maximize the transfer, and vice versa. So in this case, just to give a reference starting value, we will give 2 weights, the pressure losses and the transfer. So we are telling the software that we want to maximize the transfer. I give it a weight of 500, which is telling the software we want to give a higher priority on a transfer in this case. With this optimization is a bit more complex than this one, but of course, I don't want to annoy you with a longer explanation. So in case you have more questions, please feel free to reach out after or at the end of this deep dive session. One very interesting thing, of course, is that, as we were mentioning before, Tofy started as Tofy AM, and then we transitioned to Tofy X. So the first part of the company, Tofy AM, was clearly symbolizing a strong direction toward additive manufacturing. So in the beginning, when we started using Tofy, the idea was to support customers or companies using additive manufacturing to exploit the freedom that could be achieved using that methodology to bring to life more efficient components. So the idea is that, okay, we have this great process, we have these great manufacturing capabilities, how can we exploit this freedom? But as we grew as a company, we realized that actually the market is moving in several different directions. So not all companies are adopting additive manufacturing. So the idea is that we want to transition from AM to X. We want to expand it to extend our capabilities and also to open to, I would say, the unknown. So probably the X is symbolizing this as well. And we are opening now to several manufacturing processes. The idea is that we don't want people to necessarily change the way they manufacture, but it's more about adopting new tools to change the way they design. So the idea is that you have a manufacturing process. How can we optimize the output of this manufacturing process with a new software? As you can see, that's why we have these design and manufacturing constraints sections. Mainly, we are splitting them in between additive constraints or machining. So we have these two processes for now, but we are adding more and more moving forward. Just to give an example, for the additive process, we can define, for example, minimum feature size. So we know that additive manufacturing process have resolution, so we don't want to get too small. That might be not printable, or maybe we know that maybe when the thickness of a design, if we think about heat exchangers, when you have a too small thickness, maybe this would be a bit too porous, so you might have the fluid going from one side to the other, something that we want to avoid. So this is something, a feature we can control. We can define just by enabling this control what is the minimum feature that is allowable as a result in the final design. Similar thing we have for the channel clearance. So we know depowdering is something quite critical for 3D printing, and of course overhang is probably the main thing. So we want to be able to specify a direction. So in this case, for example, we could identify a build direction going to the direction of the negative z-axis. So we could say 0, 0, -1. Identify the bottom region, which is the one that is supported, and then we could specify, for example, a minimum or a maximum overhang angle. So we know that at the end of this optimization process, the software will be not overhanging above the value we specified. On the other side, we have machining constraints. So for example, we can identify a milling direction. And in this case, again, you can provide an axis to specify how the milling will be removing material from the block of solid that you are providing. Once everything is set up, you have a few additional things you can set up into the configuration, but very simple. You go here, you click on this icon, and you can select the computational power you want to allocate for the software to run the setup and to run the optimization. In the menu, you have here a few options, like select, for example, 8 CPUs. Again, these CPUs are not local, are not something you have to own. Everything is happening in the cloud. We are hosted on Amazon Web Services. And once you click launch, the software will give you this menu telling you that it's running, good sign. And then it's going through the different stages of meshing, running the first simulation to initialize the problem. And then we start a design phase. So you can also keep track and follow. Now, as you can see, it was very quick to set up an optimization. So we only had to specify and provide a design space, in this case, just the shape, the overall shape of the space we have available for the liquid cooled heatsink. We had to go through the setup of mesh simulation and design settings. But what we are getting here as a result is a single design. Typically, what we want to do in this phase, when we are exploring the possibility we can get with ToffeeX, the best thing is to explore a variety of different settings and parameters. This is very quick and very fast to do in ToffeeX. So, for example, here I have set up my mesh and simulation, and I'm happy with them. So I know that the simulation parameters will stay the same throughout the different design stages, and that's because these are my conditions. And I'm happy with the mesh resolution. What I want to change is, for example, the design settings. So I want to test, what if I use a different overhang angle? What if I use a different minimum feature size? What if I use, instead of additive, I go for manufacturing with traditional tools, so I go with machining? What if I use less or more material? What if I use different materials? So how can we quickly explore this broader design space? How can we, instead of making incremental improvements, start by generating a lot of designs, and then on the one that we like the more, keeping on iterating just to get to a better optimum? It's very simple. What we have to do is to simply create a new run. In this case, again, a design. As you can see, the software in this case will give us the option to select and reuse pre-existing settings. In this case, we will be happy to reuse simulation and mesh settings while we want to change and duplicate design settings for the design itself. In this case, I will click on create, and the software will give me a new design. And as you can see, I won't be able to modify mesh and simulation parameters. They're fixed. So what I can do here is instead to change the output that I can get using different design parameters. In this case, for example, let's put as off the overhang constraint, and let's instead enable the milling constraint. In this case, I want the software to remove material in this direction. So I have to identify 001 axis direction. So removing material from top to bottom, and click on update. Very simple. I change one parameter. I go on the open run icon again and click launch. So as you can see, the mesh before was completed. So the software is reusing the mesh settings. Unfortunately, the simulation wasn't done yet. Even if the software is very fast, it's not like 3 seconds simulation. But then it's reusing the same settings to perform a new design. So here you can see how it's very quick and easy to explore a design space by quickly changing one parameter and getting to a new design solution. Of course, I have already run some of these designs, so I want to show you the results of it. I'm probably going a bit longer on the time than expected. But here we have two examples. So one is the maximization of the transfer without any constraints applied. So you can see this is the structure that the software is giving as an output. So this was the starting point we had, similarly to what we've done so far. If I go in wireframe, you will see that this is the internal structure the software is building, and you can also visualize the fluid region. So you can see how the software is splitting, let's say, the fluid coming from the inlet to the bottom of this bottom region where the heat is applied to maximize the heat transfer and to cool down as efficiently as possible the structure. The result I'm showing you is without any constraints on manufacturing, so kind of giving 3D freedom to the software. But if we look instead at the design that we got by milling, we can see for the same parameters, so same ratio of pressure losses with heat transfer, we can see that we have a completely different design. So in this case, the software is carving out material from a block of solid and giving us a result which is at this point manufacturable by milling. I would like to actually share this very quickly, these results in ParaView, which is a post-processing tool we typically use. So I might be sharing, again, the screen, just very quickly. And let me go back to the screen. Okay, it was at the bottom. Here we go. So here we have a comparison of these three different designs. On the extreme right, we see the baseline design. So what was done previously, what we could design by just using our invention and our ingenuity. So in this case, a classic M-shaped channel to go down the CPU at the bottom. In the middle, we see the structure that is being optimized with a kind of unconstrained approach, so without adding any manufacturing constraints into consideration. And here instead, on the left-hand side, we are including the manufacturing constraints of milling. So you can see the streamlines, how the fluid is moving into the different structures, and also we can have a look at how this behaves. So if we visualize the temperature at the bottom of each of these devices, so here, for example, you can see that we have a maximum temperature of 311 Kelvin. If we go to the optimized region, which is slightly more unconstrained, we might be expecting a slightly lower temperature. So you can see from the legend, slightly lower. And if I rescale on those values, we see roughly 1 degree colder. And finally, we have the serpentine design. Again, let's plot the temperature for this one. Let's rescale. And you see 314, quite not uniform distribution for temperature. So we can see how effectively the software is giving a design which is optimized, which is behaving better on the heat dissipation. But also, if we have a look at the values for pressure, we will see that we also have a kind of same pattern where we have, for example, for pressure, we have a value of almost 2000 Pascal. This is a small device, just to remind you. In the IAM case, we have a value of, lower, 243, and similar value we are expecting also for the mid geometry. So yeah, this was a pretty quick overview, but it's showing you the difference in the designs that you can get in Tofy X very quickly by only changing a few parameters. You can tap into a very vast design space, so you can pick up several alternatives. So you are not limited into a design cycle which is incrementally improving on something that was either pre-existing or into something that you had to come up from scratch, and then you had to run a lot of validations. So to see what was working, what was not, and then to slightly improve and modify until you reach a convergence to satisfy the requirements. So this saves a lot of time. So in a few hours, if I go back to the software, you will see this design is taking roughly 1 hour for the set of parameters we selected. So it's really quick to get to different designs, different shapes, and then based on the results you get, it's a first iteration, you can also refine until you reach to a convergence where you are satisfied with all the results that you're getting at the end of the process. And of course, this is done not anymore in months, but it's taking just a few weeks. So we have testimonials from customers going from the conceptual design to actually manufacturing the design in 2 weeks. So it's really powerful. And we probably believe that is a great tool to start integrating into the design workflow.
Really good.
So yeah.
So excellent. So now it's time for the questions. We had one question from Ant in the comments saying, can Tofy X provide design optimization for structural and FEA problems as well? Or is it only restricted to CFD and thermal?
For now, it's restricted to CFD and thermal. So we have constraints that we can include to account, for example, for the minimum thickness of the part. So this is something that maybe you know that your design can't withstand pressure loads unless it has a minimum thickness. That's something we can control. However, we are not performing structural optimization. The main reason is that we believe our product is quite unique in what we do, and this is our main selling and our main strength. There are so many players in the market doing structural optimization, and there is no reason to compete with them. In our future, in the vision we have, the reason why we will be starting using also and implementing also structural topology optimization is when we start thinking and looking at fluid structure interaction. So to give a more complete optimization. But at this time, we are offering only fluid and thermal optimization.
I think that makes sense. Also a strong positioning from your side to try not to be a jack of all trades, which is good. How can anyone interested in Tofy?
Yeah, absolutely. We are always happy to take your queries. So if you go on the website, you can book a demo with one of our engineers or our sales guy. Very friendly, so don't be scared of reaching out. We can spend 30 minutes or 1 hour going through what are your typical applications and discuss how Tofy can be a right tool for you.
You showed us one application today, Anto. What are some of the other applications some of your customers or users work on a day-to-day basis or like on a weekly basis?
I'd say that the liquid cool heatsink is a pretty good example, and that's because it's showing how you can optimize at the same time both the fluid and the thermal aspect. But in general, the applications we tackle are very broad. So every time you have the need to optimize for improving the thermal efficiency or even the fluid delivery inside your system, your components, you can use Tofy X. This means that you can use it for heat exchangers, for manifolds, for mixers, for heat sinks, as we've seen. So the applications is really, we tackle a lot of different applications. It's a very broad scenario.
That's great. And I think you talked a little bit about the roadmap, Anto. What are some of the future developments you guys are planning on?
I hope I don't say too much or too secret things, but in general, what we are working on now is to improve on the constraints we have for manufacturability and to add more and more. So as I was mentioning, manufacturability for us is becoming paramount because we don't want these designs that we generate using the software to just be pretty pictures. We want them to be something users and designers, engineers can really put into production and see the benefit of using topology optimization into real life application. There is a kind of, people usually are skeptic about this because it's been a lot of years where TO has been over-promising maybe, but underachieving. So our promise now is to deliver designs which are manufacturable and more efficient than what could be designed by a classic, let's say, design approach.
Yeah, I think some of the things that people are also interested in. So you showed us something that, for example, comes from a specific manufacturing constraint. You would be able to then export that CAD model and just put it into production. Is that how it works? Or how does the workflow look in more detail?
At the moment, we can export STL file as an output. So people will be able to get a mesh file as a result of the optimization. We are very soon releasing also a step export, which we know it's very important for customers typically to integrate the part into the PLM systems. So this is something that is coming very soon as well. But the other format that you can get is a DTM file, which I was showing you before, can be opened with Pietropaoli, for example, which is an open source tool. So yeah, it's pretty, we have some flexibility on the export formats, but in general, our customers are pretty happy with the file they get out of the software. They are able to take them, to manipulate them, and then maybe to use them as a starting point for further simulations into maybe their systems. Because maybe here I showed you how to optimize a component, but then you want to test it in the whole system. So we are also trying to maximize the compatibility and interoperability with other software.
That sounds great. Excellent, Anto. Thank you so much for the demonstration today. I'm sure there will be a second and maybe a third part of the deep dive series with maybe a different use case. But again, guys, if you have any questions, ToffeeX.com is the address to look to get more information about the software, maybe book your demo call with the team. And yeah, if you have any more questions, reach out to Anto. I'm sure he'll be more than happy to answer your questions.
Yeah, absolutely. Thanks, Jousef. Thank you very much for today's session. It's been real fun. And yeah, as Jousef was saying, please feel free to connect with me or with the team. Just let's discuss how Tofy X can be the right tool for you. We'll be also attending a number of different events in the next few months. So be sure that you're following the page so you can stay connected and just be updated with the latest news. So maybe we might also meet in person and have a more personal chat. But thank you, everyone. It's been a pleasure. And yeah, looking forward to the next one.
Thanks, Anto.